Space is not the silent void you think it is. We look up at the night sky and see a profound emptiness, a dark and endless ocean of nothing separating the stars. This is the common perception, the quiet stage upon which the cosmic drama plays out. But modern physics reveals a truth far more astonishing. The vacuum of space is not empty at all. It is a seething, dynamic, and incredibly active medium, perhaps the most active substance in the entire universe. By the end of this journey, you will understand why the very fabric of nothingness holds the keys to reality itself. We will explore how empty space creates particles, fuels the expansion of the cosmos, and challenges our deepest ideas about existence. What if everything you see, including yourself, is just a ripple on the surface of this hidden ocean? How can nothing be the source of everything? This is not a minor correction to a textbook. It is a fundamental shift in how we see the world. Are you ready to question the nature of nothing? Our entire understanding of reality is built upon a simple foundation, the idea that nothing means nothing. For thousands of years, this was not just a casual thought, but a cornerstone of philosophy and science. A vacuum, in this classical sense, is the ultimate absence. Picture a perfect sealed glass jar. You pump out every last atom of air, every speck of dust, every trace of water vapor. Inside that jar, you are left with a region of pure emptiness, a void where matter and energy simply do not exist. It is a perfect stillness, a silent stage where nothing happens because there is nothing there to act. This view is deeply intuitive because it mirrors our everyday experience. When we empty a room, we remove the furniture and the people. When we drink the last of a glass of water, we see an empty glass. Our brains are wired to perceive the absence of things we expect to see. So for centuries, scientists and thinkers applied this logic to the cosmos. Space was the container, and the planets and stars were the objects within it. The container itself was presumed to be inert, passive, and truly empty. This belief was so strong that it influenced everything from the physics of motion to the very geometry of the universe. It created a clean, understandable picture, a cosmic theater with a dark, static backdrop. But this elegant picture is an illusion, and the shattering of this illusion did not come from peering deeper into space with a telescope, but from looking inward into the heart of the atom itself. The discovery that would unravel everything began not with the vast, but with the impossibly small. The first crack in this elegant illusion of emptiness came from a principle so strange it seems to defy common sense. It is called the Heisenberg uncertainty principle, and it states a fundamental rule about reality at its smallest scales. You cannot know everything with perfect precision. More specifically, you cannot simultaneously know both the exact energy of a system and the exact time for which that energy exists. This is not a limitation of our measuring tools, it is a built-in feature of the universe itself. Think of it like trying to take a perfectly sharp photograph of a hummingbird's wings in mid-flight. If you use a very fast shutter speed, you freeze the motion and see where the wings are, but you lose all sense of their blurring speed. If you use a slow shutter, you capture the flow of motion, but the wings themselves become an indecipherable smear. You cannot have perfect knowledge of both position and motion at the same instant. The quantum world operates under a similar but far more profound constraint. This principle has a stunning consequence for the concept of a perfect vacuum. If we demand that a region of space has exactly zero energy for any measurable amount of time, we are claiming perfect knowledge of both its energy, zero, and its duration. The uncertainty principle says this is impossible. Therefore, even in what we call empty space, the energy cannot be precisely zero. For vanishingly brief moments, borrowed from the uncertainty of time itself, energy can fluctuate. It can briefly rise above zero, and in the realm of quantum physics, energy and matter are two sides of the same coin. So what does this borrowed energy do? It spontaneously creates something from nothing. These are quantum fluctuations. Every single point in the vacuum of space, everywhere in the universe, is a simmering sea of these temporary events. Particle and antiparticle pairs, like electrons and positrons, flicker into existence for a time span so short it is almost incomprehensible, then annihilate each other and vanish back into the void. They are often called virtual particles, not because they are not real, but because they are ephemeral guests at the cosmic party, appearing and disappearing before any conventional instrument could detect them directly. This is not a rare or special event. It is the vacuum's default state, its baseline hum of activity. The void is not still. It is a frenetic, bubbling foam of creation and destruction happening everywhere all the time. This means the stage of the universe was never empty or passive. It was and is fundamentally alive. These flickering particles are merely the surface foam on a far deeper ocean. To truly grasp the vacuum's nature, we must look past the particles themselves and understand what they emerge from. The universe is not fundamentally made of tiny, solid balls of matter. Instead, it is woven from something more abstract and far more pervasive: quantum fields. Think of the entire cosmos not as a collection of objects in a box, but as a vast, living canvas. This canvas is not blank. It is etched with an intricate, invisible pattern of fields, one for every type of particle we know. There is an electron field, a quark field, an electromagnetic field, and others, including the famous Higgs field. These fields are not located in space. They are the foundational layer of space itself, a complex tapestry that permeates every single point in reality. What we call an electron, for instance, is not a solitary speck. It is a localized knot of vibration, a tiny excitation in the universal electron field. The particle is just the visible manifestation, the note played on the instrument. The field is the instrument itself, present everywhere, waiting to be plucked. This changes everything about our idea of emptiness. A perfect vacuum, in this new view, is not the absence of the fields. That is impossible. The fields are always there. They are the fabric of existence. A vacuum is simply the state where all these fields are at their absolute calmest, their lowest possible energy setting. But here is the crucial twist. Because of the quantum rules we just discussed, this lowest setting is not zero. It is a seething, restless calm. The fields are never completely still, never truly switched off. They are in a constant state of quantum jitter, vibrating with this inherent, irreducible energy. This is why particle pairs can blink into existence. They are brief ripples drawn from the endless hum of the fields themselves. So when you look at the night sky, you are not looking through an empty void. You are gazing through an unimaginably rich and active medium, a quantum plenum vibrating with potential. The stage of the universe is not a passive backdrop. It is a dynamic participant, an energetic fabric whose subtle tremors shape the reality unfolding upon it. This restless, humming baseline of the quantum fields has a name: zero-point energy. It is the lowest possible energy that a quantum system can possess, but as we have seen, that lowest point is not nothing. It is a profound and permanent something. Think of it like a simple spring. You can compress a spring, releasing energy as you do. You can also stretch it, storing energy within it. But there is a natural resting state, a middle point where the spring is neither compressed nor stretched. In the classical world, at that middle point, the spring would have zero energy. It would be perfectly still, but in the quantum world, the spring can never be fully at rest. Even at its absolute lowest energy state, it retains a tiny, intrinsic jitter, a perpetual vibration that can never be removed, no matter how cold you make it or how perfectly you isolate it. That irreducible quiver is the zero-point energy. It is the energy of the vacuum itself, the cost of admission for existing in a quantum universe. This is not a theoretical abstraction. Its effects are measurable in subtle ways, like the Casimir effect, where the relentless pressure of vacuum fluctuations pushes two metal plates placed incredibly close together. The plates exclude some of the longer wavelength fluctuations, creating an imbalance of pressure from the outside that forces them together. It is a direct physical nudge from empty space. But here is where the story takes a truly staggering turn. When physicists calculate the theoretical density of this zero-point energy permeating all of space, the number they arrive at is not small. It is catastrophically, unimaginably large. The vacuum energy predicted by quantum field theory should be so immense that it would warp the fabric of spacetime with such ferocity that the universe as we know it, with galaxies and stars and planets, could never have formed. It would have ripped itself apart at the dawn of time or collapsed in on itself instantly. The fact that we exist, that we see a relatively calm and slowly expanding cosmos, means our observed vacuum energy is at least 120 orders of magnitude smaller than the theory suggests. That is a 1 followed by 120 zeros. It is the largest and most embarrassing discrepancy between theory and observation in the entire history of science. So we are left with a breathtaking paradox. The vacuum is undeniably active, thrumming with a fundamental energy that shapes reality at the smallest scales. Yet on the grand cosmic stage, its net effect appears mysteriously, almost impossibly muted. What force or what principle is quietly cancelling out almost all of the universe's foundational energy? These fleeting guests of the quantum world are known as virtual particles. To understand them, we must abandon the idea of particles as permanent, solid things. A real particle, like an electron in an atom, is a stable, lasting excitation of its quantum field. It can be detected, measured, and persists until some interaction changes it. A virtual particle is fundamentally different. It is a temporary, fleeting ripple in that same field, a brief distortion that appears and vanishes almost instantaneously. Its entire existence is a transaction made possible by the uncertainty principle. The vacuum lends it a tiny packet of energy, but only for a correspondingly tiny sliver of time. The more energy borrowed, the shorter the loan's duration. This is why we never directly observe a single virtual particle. They are the universe's quantum whispers, spoken and silenced too quickly for any instrument to catch the individual sound. Yet their collective presence is not a ghost story. It has real, measurable power that pushes on the very fabric of our world. The proof is in a beautiful and subtle experiment known as the Casimir effect. Picture two perfectly smooth, uncharged metal plates placed in a vacuum, parallel to each other and separated by a microscopic gap smaller than the width of a human hair. In the vast sea of the quantum vacuum, fluctuations of all possible wavelengths are constantly bubbling into existence, but between the plates, only certain wavelengths can fit, like specific musical notes resonating in a pipe. The longer wavelengths are excluded. This creates an imbalance. The quantum pressure from the virtual particles outside the plates is slightly greater than the pressure from the restricted set of fluctuations between them. The result is not a theoretical prediction. It is a physical force. The plates are gently but measurably pushed together by the relentless activity of empty space itself. It is as if the silent hum of the universe has a tangible weight, a whisper that can move metal. This experiment provides stunning confirmation that the vacuum is not a passive stage, but an active participant, its hidden energy manifesting as a force we can see and measure. The virtual particles are not merely mathematical tricks, they are the fingerprints of a medium in constant creative ferment. This gentle pressure from nothing is not just a theoretical curiosity, it is a laboratory fact. The Casimir effect stands as one of the most elegant and direct proofs that the quantum vacuum is a tangible, forceful medium. To see how it works, picture that pristine vacuum chamber again, a space emptied of all conventional matter. Inside, two perfectly smooth, uncharged metal plates are positioned parallel to each other, separated by a gap so tiny it is measured in nanometers, a distance smaller than a wavelength of visible light. In the classical view of an empty void, absolutely nothing should happen between these plates. They should remain perfectly, inertly still. But the quantum vacuum is not empty. It is filled with a spectrum of electromagnetic fluctuations, virtual photons of all possible wavelengths constantly flickering in and out of existence. These fluctuations exert a subtle pressure on all surfaces, like an endless, gentle rain. Here is the brilliant twist. The narrow gap between the plates acts as a filter. Only those virtual photons whose wavelengths fit perfectly as multiples of the gap distance can exist in that confined space. The longer wavelengths, the ones that are simply too big to fit, are excluded. Outside the plates, however, the full spectrum of fluctuations occurs without restriction. This creates an imbalance. The pressure from the richer, fuller spectrum of virtual particles on the outside of the plates becomes slightly greater than the pressure from the restricted set on the inside. It is the difference between the force of a steady wind on one side of a sail and a calm breeze on the other. The net result is a measurable physical force pushing the plates together. This force has been confirmed repeatedly in experiments since the 1990s. It is not magic, it is not a theoretical guess. It is the direct signature of the quantum vacuum's relentless activity. The silent hum of empty space has a push, a whisper that can move physical objects. This means the stage of the universe is not just alive with potential. It actively interacts with the matter upon it, shaping reality in subtle, measurable ways from the ground up. But this gentle push is only the beginning of the vacuum's influence. Its hidden activity reaches into the very heart of matter, orchestrating events we once thought were purely random. Consider the humble atom. When an electron orbiting a nucleus is excited, boosted to a higher energy level, it does not stay there forever. Eventually, it falls back down, and in doing so, it releases a particle of light, a photon. For decades, physics textbooks described this as spontaneous emission, a process that seemed to happen on its own, triggered by nothing but the passage of time. It was presented as a fundamental randomness at the core of nature, but the quantum vacuum rewrites this story. That electron is not isolated in a silent void. It is immersed in the ceaseless hum of the electromagnetic field's zero-point fluctuations. Even in its lowest energy state, this field is never perfectly calm. It is filled with those ephemeral virtual photons flickering in and out of existence. The excited electron, poised at its higher energy level, is constantly being gently nudged by this background sea of activity. One of these vacuum fluctuations provides the precise trigger, the necessary whisper, to coax the electron into releasing its stored energy and falling back down. What we called spontaneous was not random at all. It was a direct response, a conversation with the active medium of empty space. The photon that emerges to illuminate our world is, in a very real sense, midwifed by the vacuum itself. This transforms our understanding of light. The glow from a neon sign, the precise frequency of a laser, the very mechanism of vision, all are processes in which the apparent nothingness of space plays an active, guiding role. The stage is not just holding the actors, it is whispering their lines. This conversation between the vacuum and matter reaches its most profound expression in a field that is not merely active, but fundamentally different from all others. While the electron and electromagnetic fields hum at their lowest possible energy, there is one field whose baseline state is not a quiet hum, but a constant, steady roar. This is the Higgs field. Unlike every other quantum field in the Standard Model, the Higgs field does not settle at zero in its natural state. Instead, it is permanently switched on everywhere at a uniform and non-zero strength. It fills the entire universe like an invisible, intangible syrup, a cosmic molasses that permeates the very vacuum we have been exploring. This omnipresent field is not a substance you can touch, but a condition of space itself, a fundamental property of the empty stage that has the most dramatic consequence imaginable. It is the reason anything has mass at all. Without the Higgs field, the universe would be a sea of massless particles zipping around at the speed of light, never coalescing into atoms, stars, or planets. The existence of structure, of you and me, hinges on this one field's peculiar refusal to be quiet. So how does an invisible field give something as tangible as mass? The process is a beautiful and subtle form of interaction. As fundamental particles like quarks and electrons move through the universe, they do not travel through a pure void. They swim through this omnipresent Higgs molasses. Particles that interact strongly with the Higgs field experience more resistance as they move. They get stuck in it, so to speak. This resistance to acceleration is what we perceive and measure as inertial mass. A particle like a top quark, which interacts very strongly, becomes very heavy. A particle like an electron interacts only weakly, so it is much lighter. A photon, which does not interact with the Higgs field at all, remains utterly massless and travels at the cosmic speed limit. In this view, mass is not an intrinsic property of a particle, like a tag attached to it at birth. Mass is an emergent behavior. It is a relationship, a dialogue between a particle and the active, non-zero medium of the vacuum. The solidity of the world around you, the very fact that you do not zip off the surface of the planet at light speed, is a direct gift from this peculiar, energized state of empty space. The Higgs field transforms mass from a simple property into a story of interaction, revealing that even our most fundamental experience of substance is woven from the hidden activity of the cosmic medium. This cosmic molasses gives substance to the universe, but the vacuum's most dramatic role is still to come. If we pull our gaze back from the quantum foam and look at the cosmos on its grandest scale, we encounter the greatest mystery in modern astronomy: dark energy. In the late 1990s, two separate teams of astronomers made a shocking discovery. By observing distant supernova, the colossal explosions of dying stars, they were measuring the rate of the universe's expansion. Everyone expected that the gravitational pull of all the matter in the cosmos would be slowing this expansion down, like a ball thrown upward, gradually losing speed to gravity. The data revealed the opposite. The expansion of the universe is not slowing, it is accelerating. Something is pushing galaxies apart from one another with ever-increasing force. That something is what we call dark energy. It is not a substance made of particles. It is not a force field in the traditional sense. The leading and most compelling interpretation is that dark energy is a property of space itself. It is the energy of the vacuum manifesting on a cosmic scale. Think back to that troubling calculation, the one that predicted a vacuum energy so immense it should tear reality apart. While the number was catastrophically wrong, the underlying idea may be profoundly right. If the vacuum possesses a small, positive energy density, a tiny amount of energy in every cubic centimeter of nothingness, then as the universe expands, it creates more space. And with more space comes more of this intrinsic vacuum energy. Unlike matter or radiation, which dilute and weaken as the cosmos grows, the energy density of the vacuum remains constant. This constancy has a staggering gravitational consequence. In Einstein's theory of gravity, energy and mass are equivalent, and they warp spacetime, creating what we feel as gravity. A constant energy density spread throughout space does something counterintuitive. It generates a repulsive gravitational effect. It acts as a kind of cosmic antigravity, pushing the fabric of spacetime apart from within. So the silent, seething activity of the quantum vacuum, the same medium that gives particles mass and pushes metal plates together, may be the very engine driving the accelerated expansion of the entire universe. The most subtle feature of empty space is shaping the ultimate fate of everything. Yet this elegant idea of a vacuum-driven cosmos collides with a problem of almost absurd proportions. The energy density we observe from dark energy is incredibly small. Measurements from the cosmic expansion tell us its value is about 120 orders of magnitude smaller than the simplest calculations from quantum field theory would suggest. To grasp the scale of this error, consider the entire observable universe. Now, imagine trying to predict the weight of a single proton. Your theoretical calculation suggests the answer should be the weight of the entire cosmos. That is the level of mismatch we are confronting. It is not a minor rounding error. It is the single greatest discrepancy between prediction and observation in the entire history of science. Physicists call this the cosmological constant problem. The cosmological constant was a term Einstein originally inserted into his equations to allow for a static universe, a fudge factor he later called his greatest blunder. Ironically, it now appears to describe the accelerating expansion driven by dark energy, a genuine feature of reality. But its observed value is so vanishingly tiny compared to the theoretical expectation from the quantum vacuum that it feels like a cosmic joke. It implies that the furious, seething activity of virtual particles and zero-point fluctuations we have been discussing somehow produces a net gravitational effect that is almost exactly, but not perfectly, zero. It is as if the universe's most active medium is performing a balancing act of unimaginable precision, where the positive and negative contributions from the quantum foam cancel each other out to one part in a number with 120 zeros. This is not just a puzzle, it is a screaming clue that our understanding of gravity and quantum mechanics, when combined, is profoundly incomplete. The vacuum is active, yes, but its ultimate influence on the shape of spacetime remains one of the deepest, most humbling mysteries in all of human knowledge. The most spectacular performance of the vacuum may have occurred before the first star ever ignited. To understand the universe we see today, with its vast webs of galaxies stretching across billions of light years, we must confront a puzzling fact. The cosmos is remarkably uniform. No matter which direction we look, the distant universe has the same temperature and density to an extraordinary degree. This is deeply strange. In the classic Big Bang model, regions of space now on opposite sides of the observable universe were once far too distant to have ever been in contact, to have exchanged heat and reached equilibrium. It is as if two strangers in separate, isolated rooms spontaneously decided to wear the exact same outfit down to the last thread. This cosmic uniformity demanded an explanation, and the answer proposed was a phenomenon of almost unimaginable ferocity: cosmic inflation. The theory suggests that in the first fleeting fraction of a second after the beginning, the universe underwent a period of exponential expansion. Space itself did not just grow, it ballooned at a rate far exceeding the speed of light, stretching a subatomic volume of primordial chaos to a size larger than our entire observable cosmos in less than a blink of an eye. This incredible growth spurt smoothed everything out, ironing any initial wrinkles into the uniform canvas we detect in the ancient afterglow of creation. But what could possibly power such an event? The engine was not a fiery explosion, but a special state of the vacuum itself. Theorists propose that a hypothetical field, called the inflaton field, temporarily became trapped in a state of extraordinarily high energy. Picture a ball resting at the very peak of a steep hill. This is an unstable, high-energy configuration. In this state, the inflattened field filled the infant universe with a false vacuum of immense density, and according to Einstein's equations, such an energized vacuum generates a powerful repulsive gravity. This repulsion did not push matter apart, it pushed the very fabric of spacetime apart, driving that runaway, exponential expansion. For that brief, pivotal moment, the vacuum was not a quiet hum or a gentle push. It was the dominant force in existence, a cosmic powerhouse shaping the entire future of reality. Then, as all such unstable states must, the inflattened field rolled down its energy hill, settling into its calm, low-energy state. The energy of that false vacuum was released in a torrent, reheating the universe and filling it with the hot soup of particles that would eventually become everything we see. But inflation did more than just smooth and expand. In its final moments as the field relaxed, quantum jitters within it, those inevitable fluctuations from the vacuum's restless nature, were stretched from microscopic to cosmic size. These tiny, frozen ripples in the fabric of spacetime became the gravitational seeds for all future structure. Every galaxy cluster, every spiral arm, every planet owes its ultimate origin to these quantum whispers amplified to a cosmic roar by the vacuum's primordial power. The pattern of hot and cold spots we see in the cosmic microwave background, the oldest light in the universe, is a direct imprint of those vacuum fluctuations, a baby picture of the cosmos etched by the activity of nothingness. But if we could peer deeper still, past the virtual particles and the humming fields, what would the fabric of spacetime itself look like? The answer may be the strangest vision of all. At scales so unimaginably small they defy comprehension, a realm known as the Planck length, the serene geometry of Einstein's smooth spacetime continuum, is thought to dissolve into chaos. Here, the quantum fluctuations of the vacuum become so violent and extreme that they do not merely create particles, they warp the very stage upon which reality plays out. The result is a seething, turbulent froth often called quantum foam. Picture the surface of the ocean during a storm, with waves crashing and churning in every direction. Now imagine that same chaotic turbulence applied not to water, but to the underlying structure of distance, duration, and causality. At the Planck scale, spacetime is no longer a smooth, continuous fabric. It is a bubbling, probabilistic froth where the concepts of here and there, before and after, lose their definite meaning. In this frenzied sea of geometry, the vacuum's activity takes on its most radical form. Microscopic wormholes, bridges connecting disparate points, are thought to blink in and out of existence. Virtual black holes, gravitational pits so tiny they last for only a fraction of a moment, constantly form and evaporate. This is not a metaphor, it is a prediction from our best attempts to marry quantum mechanics with gravity, suggesting that empty space is not just an active medium, but a dynamically disfigured one. The arena of reality is not a fixed grid, it is a living, breathing, and fundamentally fuzzy entity, perpetually recreating itself from the quantum noise of the vacuum. This means that if you could zoom in close enough, the journey between 2 points would not be a straight line across a calm surface, but a turbulent trek through a landscape that is constantly churning, tearing, and mending itself. The vacuum, in its ultimate expression, does not merely fill space, it is space in its most raw and energetic form. This quantum churn of the vacuum holds a startling power, one capable of dismantling the universe's most indestructible objects. For centuries, black holes were seen as the ultimate cosmic endpoints, regions of gravity so intense that nothing, not even light, could escape their grasp. They were perfect absorbers, cosmic one-way streets from which no information ever returned. Then, in the 1970s, Stephen Hawking performed a breathtaking feat of theoretical imagination. He asked a simple yet profound question: What happens when the restless activity of the quantum vacuum meets the absolute oblivion of a black hole's event horizon? His answer transformed our understanding of both. Hawking realized that the event horizon, the point of no return, is not a placid boundary. It is a place of extreme gravitational stress where the fabric of spacetime is stretched to its limit. In this volatile zone, the virtual particle pairs that constantly flicker into existence throughout the vacuum face a cosmic dilemma. Normally, these particle and antiparticle partners are born together and die together, annihilating in a flash almost instantly. But at the very edge of a black hole, the gravitational tidal forces are so powerful they can tear the pair apart before they have a chance to reunite. Imagine two dancers appearing from the mist, only for a sudden, violent wind to rip one away into a bottomless pit. This is the fate of one member of the virtual pair. It falls across the event horizon, swallowed forever by the black hole. Its partner, however, is left stranded outside, suddenly without its counterpart to annihilate with. Robbed of its dance partner, this forsaken particle is no longer virtual. It is promoted to reality. It gains real energy and momentum, and it flies away from the black hole as genuine radiation. From the perspective of a distant observer, it appears as if the black hole itself is glowing, emitting a faint thermal whisper of particles and light. This is Hawking radiation. The energy for this process comes directly from the black hole's own gravitational field. The particle that falls in has negative energy relative to the outside universe, and when it is consumed, it effectively reduces the black hole's mass. So, with every escaping particle of Hawking radiation, the black hole loses a tiny, almost imperceptible amount of its substance. Over timescales that dwarf the current age of the universe, a solitary black hole would slowly evaporate, its mass dissipating into the cosmos as this faint glow, until it eventually vanishes in a final, theoretical burst of energy. The vacuum's ceaseless creativity, therefore, does not respect even the most absolute barriers. It acts as a cosmic solvent, using the intense gravity of the black hole against itself, proving that even the darkest pits in space are not silent tombs, but participants in the quantum hum, slowly returning their borrowed mass to the active medium from which it came. Hawking's insight reveals a universe where even a black hole is not silent, but the vacuum's influence grows even more personal. It suggests that what we perceive as reality depends profoundly on how we move through this hidden medium. This leads us to a startling thought experiment with profound implications, the Unruh effect. Picture two astronauts floating in the deep quiet of interstellar space, far from any star. They are in a perfect vacuum, surrounded by what appears to be absolute emptiness. One astronaut fires her thrusters and begins to accelerate at a constant rate. The other simply drifts, moving at a steady velocity. According to the Unruh effect, their experiences of that same patch of empty space will now be radically different. The astronaut who is accelerating will not feel a silent void. Instead, her instruments would detect a faint warmth, a gentle bath of low-energy particles surrounding her. To her, the vacuum has become a thermal medium, glowing with a temperature directly proportional to her acceleration. The faster she accelerates, the warmer this phantom glow becomes. Meanwhile, her companion, drifting inertially, continues to measure nothing but the cold, empty vacuum. Both are looking at the exact same region of the universe, the same quantum fields, yet one sees a shower of particles where the other sees perfect nothingness. This is not a trick of perception. It is a prediction from quantum field theory that tells us the particle content of the universe is not an absolute fact. Particles are not simply there in some objective sense. What counts as a real particle versus a fleeting virtual fluctuation depends entirely on your state of motion through the quantum fields. For the accelerating astronaut, the relentless thrust changes her relationship to the vacuum's hum. The zero-point fluctuations she sweeps through are transformed from an invisible jitter into a detectable stream of radiation. It is as if the very act of pushing through the medium of space causes it to light up around her, a quantum wake made visible. This reinforces a breathtaking idea. The vacuum is not a static backdrop against which motion happens. It is an interactive medium whose observable consequences, whether it appears empty or full of particles, are co-authored by your own journey through it. The stage responds to the actors upon it, changing its appearance based on how they move. This fluid nature of the vacuum is more than a poetic metaphor. To make sense of its strange behavior, physicists sometimes borrow concepts from the most exotic states of matter we have created here on Earth. One of the most compelling analogies is to a superfluid. Picture a liquid like liquid helium, cooled to near absolute zero. In this extraordinary state, it loses all internal friction or viscosity. It can flow up the sides of a container and over the rim, seemingly defying gravity. It forms vanishingly thin films that can slip through the tiniest cracks without any resistance. This is the behavior of a superfluid, a collective quantum state where countless atoms move in perfect, coordinated unison, as if they were a single, macroscopic quantum entity. Now consider the quantum vacuum. It too is a collective state, not of atoms, but of fundamental fields in their lowest energy configuration. The ceaseless fluctuations within it are not random noise. They represent a coordinated, albeit turbulent, quantum dance across the entire cosmos. In some theoretical models, this suggests the vacuum itself may share key properties with a cosmic superfluid. One proposed property is a kind of cosmic frictionlessness. Just as a superfluid can flow without losing energy, the fabric of spacetime may exhibit a similar lack of resistance to certain types of motion or deformation. This could provide a fresh perspective on why the expansion of the universe, once set in motion, encounters so little drag from the vacuum medium itself, allowing for the startling acceleration we call dark energy. The analogy goes even deeper with another state of matter, the Bose-Einstein condensate. When certain types of particles are cooled to ultra-low temperatures, they lose their individual identities and merge into a single, coherent quantum wave, a giant matter wave that spreads out and behaves as one object. In this condensate, what were once distinct particles become indistinguishable ripples on a shared quantum pond. Some physicists speculate that the vacuum could be viewed as the ultimate Bose-Einstein condensate, not of atoms, but of the fundamental quantum fields. Every point in space would be part of this coherent, unified state. The particles we see, from electrons to photons, would then be like excitations or topological defects moving through this all-pervading quantum fluid. This perspective helps conceptualize how something can be everywhere at once, like the Higgs field, and how localized vibrations in this fluid give rise to everything we perceive as solid matter. These analog models are powerful thinking tools. They allow us to use the strange but laboratory-tested behavior of quantum fluids to imagine the even stranger behavior of empty space itself. They suggest that the universe's most active medium might not just be like a fluid, but could be the most perfect, the most coherent, and the most frictionless fluid imaginable, a superfluid of spacetime whose subtle currents shape the destiny of galaxies. History often teaches us not through its answers, but through its discarded questions. Over a century ago, physics was consumed by a beautiful and intuitive idea, the luminiferous ether. Scientists of the era knew that waves needed a medium to travel through. Sound waves move through air, ocean waves through water. It seemed only logical that light, understood then as a wave, must also need a substance to ripple across. They envisioned the ether as a static, invisible, and perfectly frictionless fluid that filled all of space, an absolute and immovable backdrop against which the universe played out. It was the stage, fixed and eternal. The famous Michelson-Morley experiment of 1887 sought to detect our planet's motion through this stationary ether by measuring subtle changes in the speed of light. They found nothing, no drift, no current, no evidence of an absolute frame of reference. The ether, as conceived, did not exist. This null result was a profound shock that ultimately paved the way for Einstein's theory of relativity, which declared there was no privileged state of rest in the universe. The idea of a static, material medium was elegantly and decisively buried. Yet here we are today, speaking of the quantum vacuum as a dynamic, active medium. So has the ether returned in a new form? The answer is a fascinating and nuanced no. The classical ether was a substance, a thing you moved through, like wading through a cosmic jelly. The quantum vacuum is not a substance at all. It is a condition, a state of the fields that define reality itself. You do not move through it as an external medium. You are an excitation within it. The key distinction lies in that word, absolute. The old ether provided an absolute reference frame, a cosmic North Star for motion. The vacuum of modern physics is thoroughly relativistic. Its properties, like whether it appears empty or full of particles, depend entirely on the observer's state of motion, as the Unruh effect so strikingly shows. There is no single, true description of the vacuum that all observers will agree upon. Yet, for all their differences, the intuition behind the old ether and the evidence for the modern vacuum share a deep philosophical kinship. The scientists of the 19th century were correct in their fundamental hunch that space is not nothing. They were wrong about what that something is. They imagined a mechanical fluid, but reality gave us a quantum plenum. They sought an absolute stage, but we found a participatory fabric. In a way, the dismissal of the ether was not the end of the story, but a necessary correction that cleared the path for a far stranger and more wondrous truth. The vacuum is the ether's sophisticated successor, not a static backdrop but a dynamic and interactive foundation, one that respects the relativistic rules of the cosmos while filling the void with a breathtaking, creative ferment. The search for the vacuum's whispers is no longer confined to theoretical equations. Scientists are now building exquisite machines, instruments of breathtaking precision, designed to listen to the hum of empty space itself. These are not telescopes pointed at distant stars, but delicate probes aimed at the fabric of reality in a laboratory. While the Casimir effect gave us our first tangible nudge from the void, new experiments seek far more subtle signatures, hunting for the vacuum's influence on light, matter, and time. One such frontier involves a phenomenon called vacuum birefringence. According to quantum electrodynamics, the vacuum should behave like a strange crystal in the presence of an immensely powerful magnetic field. Just as certain crystals split a beam of light into two polarized rays, the magnetized vacuum should do the same. This happens because the intense magnetic field distorts the virtual particle pairs flickering in and out of existence, making them align in a way that affects the polarization of light passing through. The predicted effect is incredibly tiny. To detect it, researchers are using some of the strongest magnets on Earth and the brilliant, pure light of synchrotrons. They aim to shine a laser through this magnetized nothingness, looking for a minuscule rotation in the light's polarization, a twist imprinted by the ghostly activity of the vacuum itself. It is an attempt to see the invisible medium by watching how it bends the one thing that travels through it perfectly, light. Another ghostly quarry emerging from vacuum theories is the action. This hypothetical particle is not a virtual fluctuation but a potential real particle, a lightweight, neutral entity predicted to arise from certain solutions to puzzles in particle physics. Crucially, actions are thought to be produced copiously in the hearts of stars and could be streaming through us in vast numbers, forming a kind of cosmic wind. More intriguingly, in the presence of a strong magnetic field, an action should very rarely convert into a detectable photon. Experiments like the action dark matter experiment use powerful superconducting magnets inside radio frequency cavities, essentially giant, tuned metal drums, listening for the faint ping of an action converting into a microwave photon. While primarily a candidate for dark matter, the action's existence is deeply tied to the properties of the quantum vacuum's fields. Finding one would not just solve a cosmic mystery, it would provide direct evidence for a new layer of activity woven into the vacuum's fabric. Perhaps the most ambitious hunt aims for the source of the churn itself, the quantum foam. If spacetime is a turbulent sea at the Planck scale, then even over larger distances, its frothy nature might leave a faint statistical fingerprint. The idea is that this fundamental graininess would cause light traveling through it to accumulate tiny, random variations in its arrival time. To test this, scientists are turning to the most precise rulers ever conceived, interferometers like those used to detect gravitational waves. These devices split a laser beam, send the halves down long, perpendicular arms, and then recombine them to create an interference pattern of light and dark bands. Any minuscule disturbance in the length of the arms shows up as a shift in that pattern. Researchers are now analyzing the noise, the constant jitter in these incredibly sensitive systems, to see if part of it matches the predicted random walk induced by spacetime foam. It is like trying to detect the texture of a sheet of paper by listening for the soft, collective rustle of its microscopic fibers. These experiments are pushing at the very limits of measurement, attempting to sense the universe's pixelated resolution not by looking at something, but by listening to the quietest possible hum of nothing. This ongoing empirical quest transforms the vacuum from a philosophical concept into a physical frontier, a medium we are just beginning to probe with tools that are themselves marvels of quantum engineering. This relentless hum of the vacuum creates a paradox so deep it threatens to unravel our understanding of reality itself. We have seen how the quantum activity at a black hole's edge leads to Hawking radiation, a process that slowly evaporates the black hole over cosmic eons. This elegant mechanism, however, contains a hidden seed of conflict between our two great theories of nature. On one side stands quantum mechanics, with its foundational rule that information is never truly destroyed. The quantum state of a system, the specific arrangement of all its particles and their properties, is always preserved in some form. You can burn a book, but in principle, the smoke and ashes contain a scrambled yet complete record of every letter on every page. The universe, according to quantum law, is a meticulous archivist. On the other side stands general relativity, which describes black holes with chilling simplicity. An object that falls past the event horizon is gone forever, its information seemingly lost to the outside universe. The black hole itself is described by only three visible traits: its mass, its spin, and its charge. It does not matter if that object was a star, a spaceship, or a library, the resulting black hole would look identical. This is the black hole information paradox. Hawking radiation appears to make the situation worse. If a black hole evaporates entirely through this process, leaving behind only a faint thermal glow of radiation, what happens to all the intricate quantum information of everything that ever fell in? The radiation Hawking described is purely thermal. It carries no specific details, no fingerprint of what was consumed. It is the cosmic equivalent of white noise. This suggests the information is irrevocably erased, violating a core tenet of quantum physics and creating a fundamental contradiction at the heart of our laws. The vacuum, therefore, is not just a medium for creation, it has become the setting for a crisis in physics. Its activity at the event horizon forces us to ask, does the universe forget? Proposed solutions to this paradox are not minor adjustments. They demand a radical rethinking of the vacuum's nature at its most extreme boundary. One profound idea is the holographic principle. It suggests that all the information describing the three-dimensional volume inside a black hole is not lost, but is instead perfectly encoded or painted onto its two-dimensional event horizon, the surface that shrouds it. In this view, the vacuum at the horizon is not a simple place of particle creation, but an unimaginably dense and active information processor. The falling object's data is scrambled and stored in Planck-scale fluctuations on this spherical membrane. The Hawking radiation that later escapes is then not random noise, but a slow, encrypted read out of that stored information. The vacuum at the boundary becomes a transformative translator, converting three-dimensional reality into a two-dimensional data film. Another, more dramatic proposal is the firewall hypothesis. It argues that to preserve information, the event horizon cannot be the smooth, gentle transition predicted by general relativity. Instead, it must be a searing wall of high-energy particles, a literal curtain of fire created by the extreme amplification of vacuum fluctuations. An astronaut crossing the horizon would not experience a quiet fall, but an instantaneous end. This idea replaces the peaceful vacuum with a violent discontinuity, suggesting that our understanding of the vacuum's behavior under such extreme gravity is profoundly incomplete. Both ideas and others like them point to a single unsettling conclusion. The serene quantum vacuum we study in laboratories may not be the same entity that exists at the precipice of a black hole. The medium of space itself may be forced into a new, alien phase by overwhelming gravity, a phase where its rules of information and energy are rewritten. Solving the information paradox means deciphering the true language of the vacuum when it is stretched to its absolute limit. This paradox forces us to confront a much larger question, one that goes beyond equations and experiments. If the vacuum is not empty, then what does nothing actually mean? For millennia, human thought has been anchored by a clear distinction between something and nothing. Nothing was the absence, the void, the silent backdrop against which existence played out. It was the canvas, not the paint. The discovery of the quantum vacuum shatters that distinction entirely. The canvas itself is made of paint. What we perceive as empty space is not an inert stage waiting for actors. It is the most prolific actor of all, the source from which particles, forces, and even the expansion of the cosmos emerge. This is not just a new scientific fact, it is a philosophical earthquake. It requires us to redefine nothingness not as an absence, but as a state of profound potential and relentless activity. The void is pregnant with being. This reframes our entire place in the cosmos. We are not isolated islands of matter floating in a dead sea of nothing. We are temporary patterns, intricate ripples and knots arising from and sustained by this dynamic medium. Your body, the air you breathe, the light from your screen, all are excitations in fields whose baseline state is this vibrant, humming plenum. You are not on the stage, you are of the stage. This perspective dissolves the old hierarchy that placed solid matter above empty space. Instead, it suggests a deep unity. The stuff of stars and the space between them are different expressions of the same underlying quantum reality. This has profound implications for our origin story. If the vacuum can, through a process like inflation, transform its immense latent energy into the hot, dense soup of the Big Bang, then the universe may not have come from a singular point of infinite density, but from a phase transition within this active medium. The question shifts from what sparked creation in the void to what changed the state of the quantum plenum. We are not the children of an explosion in nothingness, but the offspring of a transformation within something, the most fundamental something there is. This view invites a humbling yet connected sense of belonging. The same quantum whispers that give mass to particles and push galaxies apart are the substrate of your own consciousness. To look up at the night sky is no longer to gaze into a cold, alien emptiness. It is to look into the mirror of our own deepest nature, to see the quiet, creative ferment from which all stories, including our own, continually arise. This philosophical shift from void to vibrant medium inevitably leads to a tantalizing question. If the vacuum is the most active substance in the universe, brimming with energy and influence, could we ever learn to harness it? The dream of tapping into the zero-point energy of space itself has long been a staple of science fiction, a limitless power source waiting to be unlocked. While the reality is far more constrained by the unyielding laws of physics, the vacuum's subtle forces are already guiding the design of real, emerging technologies. The most immediate application lies not in grand cosmic engines, but in the realm of the vanishingly small. We have already witnessed the Casimir effect, where the pressure of virtual particles pushes metal plates together. Engineers are now exploring how to use this gentle, relentless force from empty space to create frictionless components for nanomachines. Picture a future microscopic device, a medical robot small enough to travel through your bloodstream. At that scale, conventional gears and bearings would seize up due to atomic stickiness, a problem called stiction. But by carefully sculpting surfaces with nanoscale precision, designers could use the Casimir force to levitate components, creating bearings that float on the quantum whisper of the vacuum itself. This is not extracting energy, but cleverly using the vacuum's inherent pressure as an integral part of the machine's design, allowing movement at scales where traditional physics fails. It transforms the vacuum from a background hum into an active architectural element. On a far more speculative frontier lies a concept that directly manipulates the medium of spacetime, the Alcubierre warp drive. Proposed by physicist Miguel Alcubierre in 1994, this is not a traditional engine that pushes a ship through space. Instead, it is a theoretical method of manipulating the geometry of spacetime itself, based on solutions to Einstein's field equations. The idea envisions a spacecraft nestled inside a bubble of flat, normal spacetime. This bubble would be surrounded by a ring of exotic matter, a hypothetical substance with negative energy density. This ring would contract spacetime in front of the bubble and expand it behind, effectively moving the bubble and its contents through space at speeds that could, in theory, exceed the speed of light relative to distant observers, all without violating relativity inside the bubble. The ship itself would not move through local space, the fabric of space itself would carry it. While this remains firmly in the realm of theory, it illustrates a profound principle. The ultimate mastery of the vacuum would not be about sailing on its quantum waves, but about learning to fold and stretch the canvas of spacetime upon which those waves dance. The vacuum here is not a power source, but the very material we would need to engineer. This brings us to the most persistent dream and the most profound challenge, the idea of zero-point energy as a practical power source. The theoretical hurdles here are monumental. The vacuum's energy is not concentrated like a battery. It is uniformly distributed, a vast ocean with only a minuscule amount of energy in any given cup. More critically, this energy represents the lowest possible state of the quantum fields. Extracting useful work from it is akin to trying to get a river to flow from a still lake that is already at sea level. Any device we might build would itself be part of the quantum system, subject to the same fluctuations. Most physicists consider it effectively impossible to create a machine that could consistently and reliably draw a net gain of energy from this universal baseline. The vacuum's energy is not a hidden reservoir we can tap. It is the fundamental hum of existence itself, the cost of having a quantum universe. To think we could plug into it and power our cities is likely a misunderstanding of its nature. The true technological promise of the quantum vacuum lies not in grand energy extraction, but in its subtle guidance, its geometric potential, and its role as the ultimate substrate for information. It teaches us that the future of technology may not be about conquering empty space, but about learning to collaborate with its hidden, active fullness. Yet for all we have learned, the quantum vacuum remains a realm of profound and unresolved mystery. The questions that define the frontier of physics today are not about distant galaxies, but about the hidden nature of the medium in which they float. At the pinnacle stands the cosmological constant problem, that staggering mismatch between the vacuum energy we calculate and the tiny effect we observe. It is a screaming clue that a fundamental piece of the puzzle is missing, a piece that must reconcile the frantic quantum world with the smooth geometry of gravity. Closely tied to this is the true nature of dark energy. Is it truly the constant energy density of the vacuum, or could it be something more dynamic, a field that evolves over cosmic time? The answer will determine whether the universe expands forever into a cold, thin silence, or whether some other fate awaits in the far future. Then there is a possibility that stretches the imagination to its limits, the idea of the multiverse. Some theories suggest our vacuum, with its specific, finely tuned properties, may not be unique. It could be just one stable valley in a vast, abstract landscape of possible vacuum states, each with different physical laws and constants. In this view, other universes, forever separate from our own, might exist in different valleys with vacuums that are fundamentally different mediums. This speculative concept arises from attempts to explain why our vacuum has the precise, life-permitting qualities it does. Perhaps the most fundamental challenge of all is the need for a theory of quantum gravity. We have quantum field theory, which describes the vacuum's particle-level activity with stunning precision. We have general relativity, which describes how matter and energy shape the smooth geometry of spacetime. But at the edge of a black hole or the first moment of the Big Bang, where the vacuum's quantum fury meets extreme gravity, these two magnificent theories clash and give contradictory answers. Unifying them into a single framework, perhaps through string theory or loop quantum gravity, is the grand quest. It promises to reveal what the vacuum of spacetime truly is at its most fundamental level, whether it is made of vibrating strings, woven loops, or something beyond our current imagination. These are not minor puzzles, they are the keys to the next revolution in our understanding of reality. Solving them will not just complete a chapter in a textbook, it will rewrite our story of what nothing is, and in doing so, redefine everything that arises from it. The journey from a silent void to a hyperactive medium is the most profound revision in our understanding of reality. We began by looking up at the dark sky and seeing emptiness, only to discover that every cubic inch of that apparent nothingness is a cauldron of quantum potential. The vacuum is not the absence of the stage, it is the stage itself, woven from fundamental fields in a state of restless, irreducible energy. From this vibrant substrate, particles blink into and out of existence, mass is granted through interaction, and the very expansion of the cosmos is driven forward. What we call something and what we dismiss as nothing are revealed to be different expressions of the same underlying quantum plenum. This means that every star, every planet, and every one of us is a temporary pattern, a complex ripple on the surface of this deepest ocean. The quest to understand this active nothing has become the central task of modern physics, for within its mysteries lie the answers to our greatest questions: the nature of dark energy, the unification of quantum mechanics and gravity, and the ultimate origin of everything that is. So the next time you gaze at the night sky, do not see a cold, empty void between the stars. See the universe's most fundamental and creative medium, a hidden dynamism that is the source of all that ever was and all that ever will be.